Okay, these are the notes from Tuesday, November 17th. If you are not in class, then you'll need to print out the PDF and take notes from this presentation. So what we're going to be looking at are called intermolecular forces or intermolecular attractions. And basically we're answering the question, why do some materials exist as a gas at room temperature rather than a liquid or solid? And everything has to do with the attractive forces within and between the particles. So, so far in our covalent bonding unit, we've been talking about intramolecular forces, the forces within a compound, the covalent bonds that hold one atom to the other within a molecule. So once we know what the molecules look like and whether they're polar or nonpolar, then we can determine the intermolecular forces, the attractive forces between molecules, and that's going to help us determine the properties of those specific compounds. So there are three different types of intermolecular forces. The first of which are called dispersion forces, sometimes called London dispersion forces after the guy that came up with them. A dispersion force is a weak force that results from temporary shifts in the density of electrons in electron clouds. Okay, so if you think about an atom, right, the electrons are constantly moving around in the electron cloud. At some point, there could be a temporary dipole, meaning at some point maybe all the electrons are on this side, so we have a partial positive over here, and that's going to attract another atom and cause that temporary attraction. Okay, so this is why everything can be turned into a liquid at some point, because even if it's just like a helium atom or a neon atom, there are these temporary dipoles happening at instants in time that are letting those atoms be attracted to each other somewhat. Okay, now the attractions are going to be happening between nonpolar things. Okay, this is why nonpolar things can be liquids, like I said before. So even though they don't have permanent attractions, they have these temporary attractions that cause them to cause the molecules to be held together. They are going to be the weakest of these attractive forces because they're not constant, they're temporary, so they're happening and then they're going away, and then they're happening and then they're going away. And we do see a trend with dispersion forces increasing as the size of the molecules increase. So really big molecules have a whole lot more electron clouds and are more able to have these temporary dipoles. Okay, so dispersion forces will increase as the size of the molecule increases. The second type of intermolecular attraction is called a dipole-dipole force, or dipole-dipole attraction. And this is caused by the attraction between partial charges, which means it's a permanent attraction. And so when we have polar molecules that have a partial positive and partial negative, then they're always going to be polar. And so we're going to get this attraction between the negative side of one molecule and the positive side of another molecule. Okay, so when hydrogen and chlorine are bonded to each other, the bond is really strong, and this bond is really strong, but that attraction between the partial charges is relatively weak. Okay, so we're just talking about the attraction between partial negative and partial positive between two different polar molecules. And then if we have a very specific type of polar molecule where we have hydrogens bonded to either oxygen, nitrogen, or fluorine, we get what's called hydrogen bonding. And this is going to be the strongest type of intermolecular attraction. So here you can see we have two water molecules. Okay, so the attraction between the hydrogen of one and the oxygen of the other is a hydrogen bond. It's a really strong attraction because hydrogen is so small. When its electrons get pulled away, all that's left is a proton. There's no other electrons shielding it, so it's going to have a fairly big partial positive charge. And oxygen is super electronegative, so it's going to have a fairly big partial negative charge. So we get really strong attraction. Okay? The same thing happens when hydrogen is bonded to nitrogen. We get that hydrogen bond here. Or when hydrogen is bonded to fluorine. Those are the three that can have hydrogen bonding between them. Okay, so again here our water molecules, hydrogen's here with partial positive, oxygen here with partial negative, and that would be our hydrogen bonding right there. Okay, so now we're going to look at how physical properties, and we have a bunch listed over here, how they're affected by the intermolecular forces or intermolecular attractions between types of molecules, whether they're nonpolar or polar. Okay, so when we have nonpolar things that have weak intermolecular forces holding them together, we are going to look at their state at room temperature. Okay, so for the most part, these are going to be gases, sometimes liquids, depending on the size of the molecules. Okay, but because they have weak forces holding them together, then usually they're going to, their molecules are not going to be attracted as much. They're going to be gases or liquids. If we have really strong forces holding the molecules together, then these will be liquids or solids, generally at room temperature. Now remember, we're only talking about things with covalent bonds. We're only talking about molecular compounds, molecules that have covalent bonds in them, and either polar or nonpolar molecules. So we're not talking about any other types of compounds other than molecular compounds. Okay? All right, so let's look at our boiling or melting point. If we have nonpolar things and they're held together by weak forces, then the boiling and melting points will be low. Right? It's not going to take a lot of energy to remove those molecules from each other. So they're going to have low boiling points, low melting points. As our polarity increases and the attractions between the molecules increase, it's going to take a lot more attraction to remove the molecules from each other, and we get high boiling and melting points. Surface tension for nonpolar compounds is low. Okay, the molecules are held together with weak forces, so there's not really a lot going on the surface. Strong forces, we're going to have high surface tension, and this is going to affect things like capillary action, how easily they spread out if they were on a table or something like that. So that's what our surface tension is going to look like. Now, fluidity of liquids is talking about how easily they flow. Okay, so if there are weak forces holding the liquid molecules together, it's going to be easy for them to flow. So we will call the fluidity of liquids that are nonpolar, they would have a high fluidity. Okay, now viscosity is kind of the opposite of fluidity. It's how they resist flowing. So if they have a high fluidity, then they're going to have a low viscosity. And then the opposite is true. Things that are held really tightly together are going to have low fluidity and high viscosity. So those are opposites of each other. Volatility or ease of evaporation. When you smell a liquid, if it has a really strong smell, it means it's easily evaporated. You're smelling all of those vapors. Those are going to be nonpolar things. Okay, so volatility is high when there are weak forces holding the molecules together. Those molecules easily go from liquid into the gas phase. And then when you have strong forces holding them, they will have a low volatility. Okay, solubility means if it will dissolve in something. Okay, so nonpolar things are only going to be soluble in nonpolar things. We use the term like dissolves like. Okay, so if something is nonpolar, then it will dissolve in nonpolar solvents. Okay, if something is polar, then they will dissolve in polar solvents. So water is polar. Oil is nonpolar. They don't dissolve in each other because they don't have the same attractions between the molecules. Okay, let's look at boiling point temperature and molecular weight, or how big the molecules are. Now generally you can see that as the weight of the molecule increases, the strength of attraction between the particles increases, right? So here our general trend is the bigger they are, the more strongly they're attracted to each other, so that means their boiling point will go up. Okay, now we have exceptions, and you can see there are exceptions right here. These three compounds right here don't follow that general trend. Well, what did we say about anytime compounds have hydrogen bonded to nitrogen, fluorine, or oxygen? Those three things have hydrogen bonding going on between their molecules. So those molecules are held together with a lot stronger forces than the rest of these molecules are. So these three exceptions right here are due to hydrogen bonding. They're going to have a lot higher boiling point because they have such strong attractions between the molecules. All of these things are going to have much lower boiling points because they don't have hydrogen bonding involved. And then the last thing we're going to look at is a flow chart where we will be creating a system to help us decide what type of intermolecular attraction is present in a compound. Okay, here's our flow chart. So the first thing we want to ask ourselves when we're trying to decide what type of intermolecular attraction is present is we need to know, is the molecule that we're looking at polar or nonpolar? All right, so let's say we have a sample of polar molecules. So let's go this direction on our flow chart, okay? So if our molecules are polar, then we need to ask ourselves, is hydrogen bonded to oxygen, nitrogen, or fluorine? Because if it is, then what type of intermolecular attraction do we have? We have hydrogen bonding. So some examples of this, like we've seen before, are water is an example. Ammonia, which is NH3, is an example. Okay. If it's a polar molecule but hydrogen is not bonded to one of those three, it's still polar, so we have dipole-dipole attractions. Okay, so examples of this would be things that are polar, like HCl, for example, is polar, but it's not hydrogen bonding. Or we could have something like CHCl3, okay, where that hydrogen makes the tetrahedral molecule polar, but still there's no hydrogen bonding involved. Okay. Now if we come over here to the other side of the table where we have nonpolar molecules, now we want to look at the size, because that's how we're going to differentiate between weak and strong attractions between nonpolar molecules. So we want to ask ourselves, what is the size of the molecule? All right, so let's say that we have a really large nonpolar molecule, okay? Then we're going to have strong dispersion forces holding it together. If we have small nonpolar molecules, then we're going to have weak dispersion forces.